Hello everyone, welcome the lecture Machine Learning Paradigm. Today we'll learn the main machine learning paradigms, basically the main ways machines learn from data. Think of it like different learning styles for humans. Sometimes a teacher helps you, sometimes you explore on your own, sometimes you learn from a few examples, and sometimes you learn by trying and getting rewards. By the end, you'll clearly know 4 paradigms: supervised, unsupervised, semi-supervised, and reinforcement learning. By the end of the class, you will be able to list the 4 machine learning paradigms. Define supervised learning and give a simple example. Define unsupervised learning and give a simple example. And finally, describe the difference between classification and clustering. Let's start with supervised learning. Here, the dataset has 2 parts. Inputs, called X, those are the independent variables, like features or measurements. Outputs, called Y, dependent variable, which is the correct answer we want. So supervised learning means I show the model examples with the correct answers, and it learns the relationship between X and Y. The goal is, when we give new inputs later, it can predict the output. In supervised learning, there are 2 very common task types: classification and regression. Classification means the output is a category, like spam versus not spam, cat versus dog, sick versus healthy. These are discrete values. Regression means the output is a number, like temperature tomorrow, house price, battery capacity. These are continuous values. The key idea: the model uses the training set to learn the best mapping, so it can generalize to new data. Now let's make this real with examples. If we have previous home sales, we can predict a home's price. That's regression. If we have previous loan data, we can predict if a client will default. That's classification. If we have visa applications, we might predict how many people apply next week. Regression again. And if we have medical data, we can classify whether a cancer is malignant. Classification. Notice the pattern. Supervised learning needs labels, meaning the correct output is known for training. Now let's switch to unsupervised learning. Imagine you have a basket of objects or fruits, but no labels at all. Nobody tells you what is what. What can you do? You can group similar things together. You choose a feature like shape, color, or size, then you put similar items in the same group, and repeat until everything is grouped. That's the main spirit of unsupervised learning. Discover structure in data without being told the correct answers. In unsupervised learning, we only have inputs X, and the output Y is unknown. This happens a lot in real life because labels are expensive. For example, imagine labeling millions of images or medical scans. That needs experts and time. So unsupervised learning tries to find patterns inside the inputs, groups, relationships, or strange cases that don't match the rest. Unsupervised learning can do several important jobs. It can learn how to represent data by finding statistical structure, meaning what is typical in the dataset. It can help us find the best features for visualization or clustering. It can detect outliers, meaning points that look very different from normal data. Different methods use different objective functions like keeping similar points close, or finding the most likely grouping. Here are common unsupervised learning examples. With customer profiles, we can find groups of similar customers. That's clustering. With transaction data, we can find unusual transactions. That's anomaly detection. With purchasing data, we can discover which products are often bought together. That's association discovery. So, unsupervised learning is often used for discovery, exploration, and insight. Let's look at a concrete dataset example. A manufacturing process dataset. It includes features like temperature, pressure, flow rate, time, pH level, voltage, and current. These are all inputs, measurements we can collect from sensors or machines. Now, an important question is, do we have an output label or not? If we also have something like product quality equals good or bad, that becomes supervised. If we don't have quality labels, We can still cluster operating modes or detect abnormal behavior using unsupervised learning. Here are popular unsupervised learning techniques you'll hear about a lot. K-means and hierarchical clustering, used to form groups. Gaussian mixture models and related methods, used for density estimation, meaning modeling how data is distributed. DB-scan, great for clustering and also finding outliers, especially when clusters aren't simple circles. Principal component analysis, PCA, and factor analysis, used for dimensionality reduction, meaning compressing many features into fewer meaningful components. Now we go to semi-supervised learning, a very practical approach. Here we have labels for only a small part of the data. Most data is unlabeled, so it's a mix of supervised and unsupervised learning. Step 1. We train a basic classifier using the few labeled examples. This gives us a starting model. Not perfect, but it knows something. Step 2. We use the large unlabeled dataset and the idea of similarity. The model groups unlabeled points near the labeled ones and transfers labels based on closeness or similarity. So the system learns from a small labeled set, then expands that knowledge to label much more data automatically. This is super helpful when labeling is expensive. A popular application is medical imaging. A medical expert might label only a small number of scans, because labeling thousands is slow and costly. Then a semi-supervised method uses those few labeled scans to help organize and label the remaining scans. So the key benefit is good performance with fewer labels, saving time and effort in real projects. Now let's talk about reinforcement learning. Imagine you need to cross a dark field without hitting obstacles. A simple approach is, you walk forward, if you hit an obstacle, you go back and try again with a better path next time. This is learning by trial and error. No one gives you the correct answer directly. You learn from success and failure. In reinforcement learning, we use a few key terms. Agent, the learner or decision maker like a robot or a game player. Environment, the world the agent interacts with. State, the current situation the agent is in. Action, what the agent chooses to do next. Reward, a score or feedback signal after an action, good or bad. Policy, the agent's strategy for choosing actions. Value, the expected long-term reward from a state or policy. So reinforcement learning is about choosing actions to maximize reward over time. Reinforcement learning is mainly used for sequential decision-making, meaning decisions happen step by step, and each decision affects the next situation. The model is given a goal, and it learns how to reach that goal through interacting with the environment repeatedly. Examples include robotics, self-driving decisions, game playing, and resource control problems. Let's finish with the big picture comparison. Reinforcement learning works differently from supervised and unsupervised learning. In supervised learning, we learn from labeled examples, input to output. In unsupervised learning, we discover patterns without labels. In reinforcement learning, we learn through cause and effect. We take actions, see what happens, and get rewards. The agent keeps adjusting actions until it achieves the best total reward over time. That's why reinforcement learning is powerful for control and decision problems.